In this video, I'm going to introduce you to what is known as the standard model of particle physics. So before I can do that, we first need to make sure that we're on the same page about what I mean when I say a fundamental particle. So a fundamental or elementary particle is one that has no substructure, which is to say it's not composed of other particles. So some examples of fundamental particles are the electron, photons, which are particles of light, quarks, muons, and there are many other fundamental particles. On the other hand, some composite particles, which is to say particles that are composed of other particles, are protons, neutrons, of course, larger things like atoms or a dust speck, which is composed of lots of different types of things. These are all different types of composite particles. Now, I'll note you might have thought that protons and neutrons were composite because indeed, historically speaking, for a long time, after we discovered the existence of, for instance, protons, we did think that they were fundamental particles. And it wasn't until the late 1960s that we discovered the fact that protons are actually made up of quarks and actually gluons, which hold the quarks together. So protons and neutrons are actually composite particles. So in this video, the standard model is really addressing these on the left-hand side, these fundamental particles. So that's really what we'll be focusing on. So first I want to discuss particle properties, which really are the way that we distinguish between different types of particles. And really there are just three particle properties that we care about. First is the electric charge, and then second is the mass of the particle, and third is the quantum spin. So this is the intrinsic angular momentum. So for instance, an electron is defined, this is really how we define an electron, by the fact that it has charge -e, where E is known as the elementary or fundamental charge. It has a certain mass, which is pretty tiny, and it's a spin 1/2 type particle. On the other hand, a photon, which again is a particle of light, does not have any electric charge. It's a massless particle, and it has spin 1. So the way we distinguish between whether we have an electron or a photon is based on analyzing these different properties. All right, so the standard model is sort of the periodic table for physics. It's where we sort of put all of our different fundamental particles together in a table. And this is what it looks like. And you'll notice these sort of colors are distinguishing different subcategories. So I want to sort of go through the different parts of these tables. You'll also notice for each type of particle, so say this is the up quark here, you know the mass, the charge, and the spin. And this is what I mean by each of the different particles is going to be distinguished from the others by these three properties. All right, so what I want to start by breaking down is sort of this table is actually split in two. There's this left-hand side, which are the purple and green particles, and the right-hand side, which are the orange and yellow particles. And you'll notice at the top here, it says this left-hand side are fermions and the right-hand side are bosons. So I want to first discuss these sort of two primary ways we separate our particles into two primary categorizations. So the fermions are these ones on the left. Why are these all grouped together as fermions? Well, there are several properties that they have in common. So these all have half integer spin, and actually in the standard model, they all have exactly 1/2 spin, all of the fermions that we know of in the standard model. So see the up here has 1/2, charm has 1/2 top. If you look through, they all have 1/2 spin exactly. Now, via quantum mechanical phenomenon, fermions obey a property, which is that they can never be in the same state as each other. And this sort of results as them never wanting to be near each other. And if you think about the sort of standard representation of an atom that you learn in chemistry, where electrons sort of fill these various orbitals, now you learned in chemistry that all of the electrons won't be in the same orbital with each other, but instead you sort of fill up these electron orbitals to higher and higher energy states when you're looking at the locations of all of the electrons around its nucleus. And really, this leads to all of chemistry. And this is a quantum mechanical phenomenon. The fact that all of these electrons won't just hang out in the lowest energy orbital together, but instead will sort of build outwards from there. And so the fact that an electron is a fermion really leads to everything that you learn about about in chemistry. Well, okay, maybe not everything, but like a lot of what you learn about in chemistry. All right, so on the other side, we have the bosons. So these have integer spin, which is to say 0, 1, or 2. These are all integers as opposed to half integers. So these ones in orange, you'll notice this bottom number is the spin. They all have spin 1, whereas the Higgs boson has spin 0. So that's why it's a little differentiated here. And bosons, these integer spins, are okay being hanging out together. They're okay being in the same state. So you can have a bunch of photons all in the same place together, and that just results in sort of a brighter light. Right? These are particles of light, and they're okay all being there together, and you just have brighter light if you do that. And that's so I should say this, whether they like being near each other or they don't like being near each other is one of the main sort of distinguishing features between our fermions and bosons. All right, so let's sort of break it down even further. So let's go back to our fermions. You'll notice there were the purple ones and then there are the green ones below. These purple ones are our quarks. So what are some properties of quarks? So I'll note that these were first proposed not until the 1960s. And this was because scientists were discovering a bunch of different types of particles. And it was seeming like, there were just tons of different types of fundamental particles. And this was known as the particle zoo, which was discovering all of these different particles. And so he was proposing that maybe all of these different many particles they were finding weren't actually different. They were just different compositions of the same base particle. So actually we only have a few fundamental particles, and then you can imagine making all sorts of different combinations of these 6 quarks to form then what seemed like different particles, but these were all different composite particles. So that's how we first discovered quarks. And as I said, in 1968, that's when we discovered that the proton is actually made up of quarks. And so the proton, which we thought before was fundamental, is actually a composite particle made up of quarks. Quarks, it took a long time to discover them, in part because they have never been observed in isolation. So they're only observed sort of clumped together, forming some larger composite particle. So that's why it was tricky to sort of discover that they are actually their own little individual things. And I'll say these particles are held together by what are known as gluons, which is a funny name, right? It's like glue. It's like a super glue holding them together, right? The force that holds them together, which is the strong force, the particle that we associate with that force is called the gluon, which we'll talk more about in a little bit. So again, we can now have this new picture of a proton and a neutron, which are not fundamental, but instead a proton is made up of 2 up quarks, this guy here, and 1 down quark, whereas a neutron is made up of 1 up quark and 2 down type quarks. And then you can build all sorts of different types of particles, which are composite particles of quarks. On the bottom side, we have these particles in green, which are known as our leptons. So you'll notice the familiar electron here, but then we also have what's known as a muon and a tau. And a lot of people think of these sort of muon and tau as being heavier electrons, because you'll notice they have the same spin as the electron, the same electric charge, but then they get sort of more massive as you move to the right here. And then on the bottom, we have the neutrinos. And you'll notice there's a different neutrino associated with each electron, muon, and tau, which is to say there's an electron neutrino, a muon neutrino, and a tau neutrino. So an interesting thing about the neutrinos, you'll notice that there's not an equality here for their mass, but it's just there's an inequality, and that's because we don't actually know the mass of the neutrinos yet. And actually for a long time, they were thought to be massless because they are tiny. They are, the total mass of these neutrinos is believed to be less than 1 millionth that of the electron, right? So the electron is already one of our more tiny particles, and these neutrinos are 1 millionth that of the electron. So these are very, very light guys. So leptons, all of these guys in greens, they don't interact with the strong force, which is to say there's no gluons holding them together. Instead, they interact with something known as the weak force. Heavier leptons, especially the tau, will decay very, very rapidly. And so that's why actually we didn't discover the tau until more recently, because its lifetime is so short that that was hard for us to recognize one of them. Oh, so here we go. It was discovered in the 1970s, and indeed the lifetime is 3 times 10 to the negative 13th of a second. So this is a very small lifetime. So if you can create a tau, but it's going to die pretty much right away. And these leptons are primarily what we think of as being involved in radioactive decay. So for instance, beta decay is one of the primary types of radioactive decay. This is where a neutron turns into a proton. So we have our neutron down here, which is comprised of an up and 2 down quarks. What's going to happen is, this is the weak force, which is an interaction force here. So we have, when the neutron decays into a proton, one of its down quarks turns into an up quark. And then what happens is there's also an electron and then an anti-electron neutrino, which are emitted in this process. This is an example of beta, what's known as beta decay. Okay, on the other side, we had our bosons. And so remember, we have these orange bosons first, which are all spin 1 type particles. What are some facts about bosons? Well, so these are said to be the force carrying particles. So the gluon, as I said, is the particle which carries the strong force. The photon, which is a particle of light, carries the electromagnetic force. And then the Z and W bosons both carry the weak force. And then finally, our last piece of the standard model is the Higgs boson. Now, this is our only spin 0 type particle that we know of. So it was not discovered until 2012 at the Large Hadron Collider, and this was very exciting because a lot of physics before this had sort of assumed the existence of the Higgs, and so conclusions they made based on that assumption would have been wrong had we never discovered the Higgs, but we did, so that was nice. So this is a sort of bird's eye view of the Large Hadron Collider. So this is a ring. This yellow line is representing this gigantic tunnel under the Earth. So this is the approximate position of it. And this is 17 miles in circumference, this ring. So this is very large, a very large experiment. That's the Large Hadron Collider, right? So this is a picture of what it looks like inside these tunnels. So you can imagine this is very impressive, the type of experiment that they built that is still, as a theorist, blows my mind thinking about the things that they've done here. So these are 2 people here. So you can see this is gigantic. So what happens is particles fly around this sort of tube in the middle, and all of this equipment outside here is for detection. All right, so that's how they discovered the Higgs particle, which was very exciting. So I'll mention it was first proposed in 1964, and something known as the Higgs mechanism explains why certain particles have mass. So a lot of people will sort of misquote this, saying like the Higgs causes particles to have mass. That's not the right way to think about it. Instead, there's something known as the Higgs mechanism, and there's a Higgs field, and fluctuations of the Higgs field are known as the Higgs boson. And so indeed, as I just said, the Higgs particle is really a fluctuation of this Higgs field, a quantum fluctuation of the field. All right, so that's the basics of the standard model of particle physics. These are all of the particles that we know for sure about, that have been verified experimentally, and to date, these we believe are all of our are fundamental particles. Each of them are fundamental, which is to say they are not comprised of other particles. Of course, who knows? Maybe one day in the future we'll discover that there's something more fundamental. But as of now, this is our sort of full set of very well understood, experimentally verified um, particles in nature.